Okay, well, thanks everyone. I'm Brock Palen from the University of Michigan. Here I'm going to talk about how we worked with DDN to be able to solve a number of campus storage problems we've had. Over the last couple of years, we went from having no research storage service to having over 14 petabytes of data, primarily driven by life science. But one of the things I will stress here is that we are a general service provider for our campus, and thus the multi-tenant. We've got a few thousand users of these different environments, and multi-science. Multi-science here is absolutely no joke. University of Michigan is the world's largest public research university with about a $1.5 billion research budget. Public there is the key part. And we have over 100 top 10 graduate programs. And just so we have more programs than 100 programs, but that use that as a proxy of just the sheer amount of diversity that is going on this campus and trying to support that. So we have a very large medical complex and medical school, teaching hospital, and research hospital. We have a very large engineering college, law, humanities, social science, physical sciences. We've got absolutely everything. So the challenges are supporting that. So who am I? I'm a nuclear engineer who never got a job with an actual reactor. That solar car there is on purpose. I was working on solar cars in undergrad, and my parents told me I needed a job to be able to stay in town over summer, and I found it pulling cables at the HPC Center, and that was 2004, and I've absolutely never left. Like I said, my background is actually nuclear engineering. I was supported by NPACI at that time, which was a predecessor to things like Exceed and other things, and been doing this for quite some time. So who is ARC? ARC is an office under the Office of UMOR, University of Michigan Office of Research. We have 4 different units. We represent technology services, the third one here. So we represent all the systems, the contracts with the cloud vendors and stuff like that. We bring services to our users. CSCAR is our sister group over here. They're like data scientists, consultants, scientific visualization experts. They're like services. The other 2 are the more interesting ones. Those are our academic programs and our faculty-led institutes. We have over 350 affiliated faculty between the 2. We've had a big push in data science in the last couple of years. Made a big investment there and brought a number of, provided both services and consultants, but also did a bunch of faculty hires and grants and other things like that. So how do we support all this work? Well, here's how we've traditionally done it. We shoved everybody into the same solution and said deal with it. One thing you should understand about our campus is faculty have skin in the game. They pay to use these resources. So if we made a general purpose system, it ended up being too expensive for everybody and nobody was happy. Also, we assumed that all data was the same. We assumed all data needed high performance. We assumed all data needed the same amount of protection. We assumed all data needed the same type of access patterns. That is absolutely not true in terms of faculty desires. And we started digging into this a little bit more based on a paper that came out of San Diego Supercomputing Center. And we really started to realize we had a couple different classes of data. So what do our users look like, though? So how complicated can we actually make this? Well, our users are generally novice level. They're generally new to this sort of environment. They're master's students, they're first-year PhDs, things like that. And they've got 4 years to get their PhD done and out the door, and they don't want to spend a whole bunch of time becoming computer automation experts. Also, we're generally not running leadership class systems. We have very large user counts, but we're a very modest size environment. And then, of course, our users tend to graduate. So we're training how to use these systems and how to get the most performance out of them is a continuously ongoing effort. Because by the time you finally got someone up to speed, they graduate and you got a new master's student in the door, new first-year PhD. Again, we have protected data. About half of our research budget is related to the NIH. So we have a very large amount of protected data, whether it's export controlled or patient data. And we've got open data like fundamental sciences. We have some people who have lots of files. We have some people who have large files. So we started looking at our system. What does this actually show us here? What this is showing is 99% of our files are 1 megabyte or less and only consume 4% of the disk space. About 50% of our files are 1 gigabyte or larger. So if I go back to that one size fits all, we basically make a solution that would work for billions of small files, which requires a lot of expensive flash, caching, metadata acceleration, but that drives the cost of the per terabyte way up. Cost per terabyte here is competition, right? The more data we can store for a given research budget, the more competition we have. So what did we do? We worked with DDN We designed a system that was not designed for peak performance for all cases. It was designed for good enough performance, but a very low price point. So for those users with very large data volumes, imaging, climate, omics, lots of different things fall into this. They're basically people who have 80% of the data, but they're only 20% of our users. They're very cost sensitive to how much your storage is costing them. And so it basically says, like, look, if you're willing to not deal with small files or put that on a different system, we can cut your cost of storage by 2/3. And we did exactly that. We just announced this system. It's called Locker. We have it at 2 sites. We provide optional replication if faculty value their data, or if it's data they can reproduce and thus don't need 2 copies. They can choose whether they want to replicate it or not. We launched with 5 petabytes. About 3 weeks ago, we've got 2.2 already on it. So we got a lot of vindication here that we did the right thing for our campus. Because what did faculty do that were extensive to this? They would buy servers full of disks. They'd buy a lot of Drobos. There were a lot of self-management. We had sensitive data out there not being monitored, not being audited, in laboratory conditions, so they weren't physically secured. This system uses all self-encrypting drives. This system will support sensitive data. It's going through the compliance process right now. So, you know, your mother's medical record might be on this thing in the future, and we're doing research on it. So we want a secure environment, but we also got to be cost effective because that leads directly to competition. So encrypted at rest, we're currently 5 petabytes. We're able to expand in modest quantities because, again, if we expand too large and we have a lot of dead weight capacity, we have to somehow recover that cost because, again, we are a cost recovery operation. So we're very grateful that we can expand in reasonable increments, and they were able to come up with this solution. Now, this was meant to be bulk storage. General purpose NAS bulk storage. Get the price per spinning terabyte down as low as possible. DDN normally talks about performance. Turns out they can do more for you. The SFA architecture is very good at being able to do this scale out with minimal excessive additional things like CPU, ports, memory. But DDN also recently won an award from us to be able to build our brand new scratch file system for our new cluster called Great Lakes. In that case, it is a performance optimized system. It's a very different price point, but it's designed to keep up with the new compute of today. So here we're using 2 petabytes of grid-scaler 14K with about 100 terabytes of IME in front of it. And so by doing that, this gives us our high performance when you're computing. We have bulk data stored on the other system, and now we've segmented out the price points depending how fast do you need your performance, what's your data profile look like, and then we also buttress each of these systems with an archive for truly cold data. So we're very grateful for working with this. This worked very well for us. So these are all of our partners for the new Great Lakes system, which is the world's first HDR system. And you can see they put a 12K there in the mock-up, but that's actually a 14K. And we're very grateful for the support DDN's given us for that, and the other partners, Intel, NVIDIA, Dell EMC, and Mellanox. So again, this is where you can contact us. Again, we're the University of Michigan. We provide services to our entire campus, hospital, research, open science, protected data, export control. We do everything, and so we needed to figure out how to solve these problems, and DDN helped us solve that.